Hi, everyone. Let's do a little electrochemistry. So this is for Chem 26, second semester of general chemistry. And here's the PowerPoint slides provided by Professor Season. Electrochemistry. Okay, electrochemistry deals with electrons. Yeah, fancy that. And there's a particular type of reaction that deals with electrons, and that is the redox reaction. So where's my pen? I'll just point at stuff. So redox reactions, actually I do want to draw on the screen. So redox stands for reduction oxidation reactions. I'm going to use this later. So remember redox, combination of oxidation and reduction. Okay, what's oxidation? Well, remember the little memory aid, the memory mnemonic oil rig? That's a great way to remember what oxidation and reductions are. Oxidation is loss of electrons. Reduction is gain of electrons. And when one molecule loses an electron, the other molecule gains the electrons, and you can say that electrons are transferred. And so in electrochemistry, we're going to have some molecule, ion, compound, a species, chemical species, release electrons. And then before we give those electrons to the other species, the other molecule, ion, compound, whatever, we'll have those electrons travel through a wire. And then when it reaches the other side, the electrons will be received by the molecule being reduced. And as those electrons travel, that's electric current, electrical energy, and we have electrochemistry. Cool. Okay. Let's see, click on the screen. There we go. Okay. Okay, so we reviewed oxidation reduction. For agents, reducing agents, oxidizing agents, remember everything's backwards. Okay, so we got one compound being oxidized. So that molecule is releasing electrons. Well, where are they going? Somebody else who's going to receive them and get reduced. So the molecule that was oxidized is reducing someone else. Yeah, things being oxidized are reducing agents. If you're being reduced, I'm receiving electrons, I am being reduced, then I'm taking them someone else and helping them be oxidized. I'm being reduced and I am an oxidizing agent. I'm helping someone else get oxidized. Everything's opposite. Whoever's being oxidized is the reducing agent. Whoever's being reduced is the oxidizing agent. Cool. Okay, for redox reactions, it's helpful to keep track of the electrons being transferred using oxidation numbers. I'm going to abbreviate it ox number. Where's my pen? There we go. So oxidation number, I'm going to use a hashtag because it also means number. So find the ox number. So we'll have to remember that elements in their natural form, copper is a solid, that's straight off the periodic table. When the elements are in their natural state, the oxidation number, ox number, is equal to 0. The other rule or guideline is that monatomic ions, single atom ions, their oxidation number is equal to the charge. Okay, so in this reaction, well, this is actually a half reaction. It's just part of the full reaction. We have copper at oxidation number 0 going to copper 2 plus, oxidation plus 2. And what became of the oxidation number? It went from 0 to 2, and it increased. The oxidation number was increased. And that's a way to identify that the reactant, the copper in this case, was oxidized. Let's do the same thing for this other half of a reaction. It's not the whole thing, it's part of a reaction. We got copper as a +1 monatomic ion. Oxidation number is a +1 for one of these silver, Ag, atoms, ions. And then afterwards, it's in its natural state. Silver as a solid, straight off the periodic table, the oxidation number is equal to 0. And what became of the oxidation number? It went from 1 down to 0. It reduced in value. So this is reduction. You could say that this Ag plus was reduced. There you go. That's how we're going to use oxidation numbers. And then Ag plus, what kind of agent are you? It's an oxidizing agent. It's opposite, right? It's being reduced, so it must be the opposite form, the oxidation agent. Nice. Cool. Okay. Ooh, balancing redox reactions. We probably should do this because I don't know where you are in your chemistry education. Did you talk about how to balance redox reactions? Maybe you did, maybe you didn't. If you did, let's just review it anyways. And if you didn't, well, then let's do it for the first time. So you know how to balance a regular reaction, right? You just want to make sure the same number of elements are on the reactant side as the product side. Now for redox reactions, by definition, someone's losing electrons, someone's gaining, there's a flow of electrons. It's possible that the electrons may not be balanced. You have to balance the electrons. In addition to balancing the number of atoms, you have to balance electrons, and electrons carry charge. So you also have to worry about making sure that the total charge on the left side, reactants, is equal to the total charge on the right side, products. Okay, so we're balancing a lot of things, the atoms, the electrons, the charge. So there's a process to help us try and get all those things balanced. And this is how it works. If you're going to balance a redox reaction, someone's being oxidized, someone's being reduced. Okay, I'm looking at the directions here. There's not just one way of balancing redox reactions. You can find some YouTube videos that show you excellent ways of doing it, and it won't match this method exactly. And that's okay. It's okay. Just in the end, as long as the balance equation balances atoms, electrons, and charge, it's a good method. Okay, so this PowerPoint slide's outlining one method. The method I learned, the one I'm most comfortable with, is a little different. I start off by splitting the reaction. Ooh, I didn't have the pen. I start off by splitting the reaction into half reactions, right? Someone's being oxidized. Okay, so take that piece, put it off this side. Someone else is being reduced. Okay, take that piece, put it off this side. And now we have two pieces of the original reaction, and we want to balance those. What do? First, step 3 says balance each half reaction. There's 3 things being balanced here at least. Okay, split them into half reactions, and then balance the redox atom. So don't balance all the atoms. We'll save that for later. But balance the atoms whose oxidation numbers are changing. So yeah, at this point, assign oxidation numbers and see which elements are changing their oxidation numbers. And then for those atoms, make sure you have equal numbers on both sides. Balance the redox atoms. Okay, and then figure out where the electrons are transferring and how many are being transferred. And then balance that using charge. So the electrons are negatively charged. And so an oxidation reaction means somebody starts and releases electrons, so electrons will be a product. For something being reduced, well, that species, that chemical compound is going to gain electrons. So the electrons will be a reactant. And on the product side, there's not going to be electrons. So for your half reaction, one side is going to have electrons, which are negative. So I need to balance the charge, maybe by bringing in some acid, H+, or maybe bring in some hydroxide ions, OH-. They carry charge. And so for some redox reactions, it requires either a low pH, acidic, so we can have some H+, Or maybe it requires a basic solution above 7, so we have some hydroxide ions. And then we're adding H's and OH minuses to balance the charge. Well, now we have to balance the hydrogens and the oxygens, probably by adding in some water. And once you get those half reactions balanced, you need to adjust the number of electrons so that when you recombine them, the electrons cancel out. And then finally, check and see that you did it right. Check the atoms and the charge. Did you get all that? No, me neither. Let's just do one. Make it a little more clear. Oh, whoops, I forgot to start the program. Hey. All right, let me use paint. And I want lots of room. So let's make it a little bigger. Sorry, I forgot to start screen sharing. Let me finish setting up. And then I'll share the screen. Almost there. Good. All right, let's go back to PowerPoint. No, go back to Zoom. Hi. And then go here. Good. All right. I forgot to zoom out. Good. Ooh, that's too far. I got the pencil. Good. So suppose the question was a sample problem. Balance this. And we're told, where's my example problem? Let's say we're told that some MnO2 as a solid reacts with Cl-, that's aqueous, and it forms manganese cations, aqueous, and some chlorine gas. And we're told it's in an acidic environment, an acidic solution. And now we have to balance it. Okay. My gut is saying, well, just see if you can just balance the atoms. Well, there's some O's over here. There's no O's over there. So that's a problem. The other thing that's happening that's a little less obvious is that the oxidation numbers are changing. Chloride has an oxidation number of a -1. And then the chlorine atoms over here, it's in its elemental form. This is chlorine right off the periodic table. Natural chlorine pairs up, it's diatomic. The oxidation number of each chlorine atom is 0. And so it's changed. Specifically, it went from -1 up to 0. It increased. It didn't get reduced, so it's being oxidized. Yes, this is an oxidation reduction reaction. So you simply can't just balance the Cl's, the O's, and Mn's. You may not get the right answer. It's a redox reaction. It's a process. So step 1, split into half reactions. Well, Mn is +2 here. What's Mn before? Well, go back to how we calculate oxidation numbers. And remember that when oxygen is making a bond, well, is it ionic or covalent? Let's start there. Manganese is a transition metal. Oxygen is a non-metal. Usually non-metals bond to metals through ionic bonding. So what's the charge on oxygen when it's ionic? -2. And there we go. Now we have a monatomic ion. The oxidation number for these oxygens is -2. And now the rule is to calculate the oxidation number for the other elements, Mn in this case, manganese. You want to assign an oxidation number so that when you add up all the oxidation numbers, it equals the overall charge. Okay, and the overall charge, there's nothing here. There was something here. There's a net -1 charge. This thing has a -1 charge. This doesn't have a charge. The total charge of MnO2 is 0. So what's oxidation number when you subtract 4 gives you 0 of +4. Okay. There's no oxygens over there. Realize that manganese is going from +2 down to, sorry, it's going from +4 down to +2. It's being reduced. This thing's being reduced. So the reduction half reaction is where MnO2 changes to Mn2+. Chloride is increasing. It's being oxidized. Its half reaction is Cl- going to Cl2. Okay, so all I've done now is split my half reactions. And then the first step is balance redox atoms. Balance the atoms whose oxidation numbers are changing. And that means leave oxygen out. Don't balance the oxygen now. We'll balance it later. Okay, so there's one Mn on both sides. This is already balanced. Ooh, but there's only one chlorine atom on this side. So let's put a 2 in front of it. And now I've balanced my redox atoms. Next, balance electrons. Really, you're balancing the oxidation numbers. What does that mean? Well, we just said that Mn starts at a +4, and Mn2 plus is now at a +2. So the oxidation numbers don't match. Yeah, because it's being reduced, it's reduction. But how did it get reduced? Where are the electrons that Mn is gaining? And how many of them? Well, 4 minus electrons, because electrons are negative. Or you could say that the oxidation number of an electron is -1. That works. If I want to go from +4 down to +2, I need to subtract 2 from this. Or I need to use 2 electrons. Mn needs to gain 2 electrons, so it takes it from +4 to a +2. And so that's really balancing the oxidation numbers by using electrons. What about over here? Each chlorine atom started at a -1 oxidation number and went to 0. They're kicking out electrons. They're losing this negative electron and being oxidized. But there's 2 chlorines. So I have a total of 2 electrons being ejected, or the chlorine anions kicking out 1 electron each for a total of 2. And now this is explaining oxidation. You start with something and out comes electrons. The chloride lost them. MnO2, well, you brought in electrons. Mn ate them up and became Mn2 plus. The Mn manganese gained 2 electrons. That's reduction. Okay, now we have to balance charge. So what's the charge on the left side of the equation? Well, the MnO2, the whole molecule has a 0 net charge. 2 electrons brings the total charge on the left side to -2. Wait a minute, but on the right side, it's a +2. So how do you balance that? Well, we're told it's an acidic solution. So there's a whole bunch of H pluses in the water mixed in with these reagents. So bring some in. Okay, so which side of this equation, if I put in some H pluses, will make things equal in terms of charge? This side. Let's bring in 2 H pluses to cancel out the 2 minuses. And now, right now, temporarily, the left side has a net charge of 0. 2 electrons, the charge cancels out the 2 pluses. Wait, but this side has a net +2 charge, so I actually need to bring 2 more so that now both sides have the equal number of charges, right? This adds the +4 and a -2. 4 minus 2 is a +2. Hey, charge is balanced. So now our half reaction looks like this. And we'll check the charge one more time. No charge, 2 times a minus is a -2. 4 times a plus is a +4. 4 minus 2 is a +2. Yes, that matches this side +2. Over here, we have a 2 minus. That's a 0 for chloride, a chlorine molecule, and we have 2 minuses. Hey, it's already balanced. Beautiful. Oh, what if this was not an acidic solution, but it was a basic solution? So let's change the pen color. This is, you don't have to do this here, but just for reference in the future, we started with this reaction and we had the balance of charge. And suppose we're told it was a basic solution, which means we have some hydroxide ions in solutions. On this case, you want to put the hydroxide ions on this side. So add 2 hydroxide ions, so +2 cancels the -2. So now there's a 0 charge on this side. Oh wait, but there's 2 electrons on this side, so you actually have to add 4 hydroxide ions over here. So if you look at the charge, it's 2 minus 4 gives you a -2, and that balances the charge on this side. So then your half reaction would look like this. That would be your half reaction if the solution was basic. Cool. All right, last step, dealing with half reactions anyways. So now we want to balance all atoms. Basically the hydrogens and the oxygens. All right, so let's take a look. There's 2 O's. Yep, 2 oxygens on the left side and none on the right. There's 4 H's on the left side, none on the right. Well, what's left in our solution that has H's and O's? Water. It's a solution, an aqueous solution. So we can add water to either the left side or the right side. We need to add it to the right side. Okay, if I add in 1 water molecule, that only gives me 1 oxygen, doesn't match the 2. So I need 2 water molecules. So I have 2 O's over here and 2 O's over here. Hey, and there's 4 H's on the left side and I have 4 H's on the right. Beautiful. So all the atoms, Mn is still balanced, good. Everything looks great. There's no H's or O's here. It's already balanced. All the atoms are balanced. Awesome. Cool. Our half reactions are completely balanced with atoms, electrons, and charge. Now it's time to recombine them and get the true overall reaction. To do this, we got to get rid of those electrons. So you have to make sure that they're going to cancel out. And they do. We start with 2 electrons in this half reaction, and we end with 2 electrons over here. So they're going to cancel out. Let's suppose we had a different half reaction that said, I don't know. Let's say the number was 3 electrons in here, whatever. I can't think of another example. But what I'm trying to point out, suppose this half reaction had 3, but this one had 2. The electrons aren't balancing. What you have to do then is take the whole equation and multiply it by some factor so that you can get the same number of electrons on both sides, both half reactions. So here it would be 3. If you multiply this equation by 3, you get 6 electrons. If you had 3 electrons, you multiply by 2, the whole thing, to get 6 electrons. And by multiplying, I mean you change all the subscripts by 2. You change all the subscripts by 3. Okay, but we didn't have that case. The electrons already matched automatically. So let's kind of clean this up. Yay, that's much nicer. Okay, what you do to combine them is just list all the reagents together. So it's MnO2 plus 2 electrons plus 4 H pluses. That's all the reactants here. Take all the reactants here, 2 Cls. Then take all your products, Mn2 plus, 2 waters. And then take all your products, Cl2, and 2 electrons. And then look and see if you have same things on both sides. Like there are times when you'll have some more H pluses on this side. And so you want to cancel out the extras. So if you had like 2 H pluses over here, you cancel out 2 of these and take away 2 of those, leaving with 2 H pluses. That's what you want to do. That's what you want to do. You just kind of, if the same species appears on both sides of the equation, move some to the other side. And that's what we're doing here. We have 2 electrons here and 2 electrons here, and they cancel out. So like spectator ions. And there's our overall balance equation. Probably should throw in the physical states. And we now have, ooh, almost put AQ for water, but no, water, when it's in solution, is in the liquid state. So there's our balance equation. We did a lot of work to get there. We better make sure we did it right. So let's check and make sure the atoms and the charge is balanced. Okay, so there's 1 manganese on both sides, 2 oxygens here, 2 oxygens there, 4 H's, yep, 4 H's, 2 chlorines, 2 chlorines, sweet. Total charge, I got 4 pluses and 2 minuses. That adds up to a total of +2. These things are neutral. There's a +2. Yay, charge is balanced. So it looks really good. Done. Dunny? Dunno? No, done. If you look this up on the internet or in a textbook, you might see a different version. So this is fine. If you've balanced it, you gave this to me on the exam, I would give you full credit. But to make it look like something you might see in a textbook, or actually if you go in the lab and you want to do this chemical reaction, we don't have a bottle of H pluses and another bottle of Cl minuses. No, you probably would have some HCl. Yes, you have some aqueous HCl. And you need 4 of them to get all your H pluses. You would. But that gives you 2 extra chlorines, right? You're only supposed to have 2 over here. You have 2 more. So you need to add 2 more to the other side to balance the chlorines. And guess what? That would just bond with the manganese and form manganese chloride. So you don't have to do this. I'm just saying, if you're looking this up on the internet, textbook, or if you want to do this in the lab, this is the actual balance equation that would help you get the recipe right. You need 4 molecules HCl, 1 molecule MnO2, and that'll make these molecules as products. Cool. All right, but again, I already said we're done up here. That was good enough for me. Back to the PowerPoint slides. Yay, remember where we were. Okay, so we just reviewed, or maybe taught for the first time, how to balance redox reactions. And remember, if you have learned how to do it and it doesn't match my method, that is okay. As long as we end up with the same equations at the end. And I had 2, so if you can get either one of those equations, the final balance equation, you are good. More terms, electrochemistry. Yeah, just changing chemical energy into electrical energy. We're taking the electrons coming out of a redox reaction and connecting a wire in between the oxidation reaction, releasing electrons, and the reduction reaction, gaining electrons. And we put a wire so we can actually transfer electrons. Electrons move from one side to the other, and that's an electric current. Use that electricity to do work. Okay, there's 2 batteries, 2 types of cells you can create. The normal one is a galvanic or voltaic cell, and that's just spontaneous. You got an oxidation reaction, you got a reduction reaction, and electrons naturally flow. The reaction's spontaneous. All is good. However, it is possible to set up the reverse reaction where things are not spontaneous, and you can force it to go. That's called an electrolytic cell. That's where you apply voltage. You plug in the reaction into the wall using electricity from an outlet or from another battery. Use electric current, and you force the reaction to go in the direction where it doesn't want to. It's a non-spontaneous reaction, but you can force it to go. Very cool. Talk about getting what you want. All right, we're going to deal with volcanic cells, galvanic cells. They go by 2 names, voltaic, galvanic. The forward spontaneous type of cell, like a battery. Okay, so you could make a battery using zinc and copper. This is not a battery though, because the reactions are not separate. We're doing all the reactions in one system. So we got a piece of zinc metal in copper solution. So you can see how the solution's blue from the copper 2 plus. Whoops. Sorry, tap the screen. Went to the next slide. Okay, copper plus 2 ions absorb red light. And so if you shine white light on it, all the red light gets absorbed, so you only see blue. And the darker the blue, the more copper plus 2 ions in solution. Okay, so what happens if you dip a sheet of zinc metal into a solution of copper ions spontaneously, all by itself? You get this situation where this is black film being deposited on the zinc metal, and the blue color is fading. Why? Well, spontaneously, the zinc will release electrons, be oxidized, and the copper will gain those electrons, be reduced, and then that change then is the zinc metal becomes zinc ions. The zinc metal starts dissolving. So underneath there, you scrape it away, you'll see that the metal is actually dissolved away, forming zinc ions. And the blue color in solution, where'd the copper go? It's this black precipitate. It turns out that copper gains electrons to form copper solid. Individual atoms sprinkled on a surface is really good at absorbing light, so it appears black. But if you scrape off the zinc and pack all the copper together and pound it together, then it'll look like a piece of copper metal, because it's solid copper. But you have to pack it all together so it looks like a shiny, coppery copper metal. And in the process, zinc is releasing 2 electrons, being oxidized. And the copper cations are absorbing, gaining electrons, they're being reduced. More terms, we're gonna make a battery. And so there's something happening, there's an oxidation reaction, releasing electrons, and a reduction reaction where they're being gained. And we're gonna those are gonna be our 2 electrodes. So if you think about a battery, well, I have one here. There's a positive end and a negative end. There's a positive electrode and a negative electrode. And we got words, terms for all this. So the electrodes, the ends where you connect your wires, those are the electrodes. One's called the anode, the other one's called the cathode. Let's get the pen out. Okay, so at the anode, that's where oxidation occurs. Okay, so remember how I said, remember the term redox? Because all these batteries, all this electrochemistry depends on oxidation reduction reactions. Oxidation reduction has a nickname, it's called redox. The red comes from reduction, the ox comes from oxidation. So my chemistry teacher taught me, hey, look at anode and cathode and take away the ode. You're left with an and cath, or maybe just cat. You always have to have a redox reaction when you have anodes and cathodes. So take the ox, which has 2 letters, pair it up with the an, which has 2 letters. So an goes with ox, and that tells you anodes are where oxidation occurs. 3 letters in red for reduction, 3 or 4 letters, depending on what you do with cathode. Cat, meow, has 3 letters. So pair that up with red, and you got the cathodes where reduction occurs. Let's go down to the last point. Take away the ode and add ion. An anion is negative, so the anode has a negative sign, just like anions have negative signs. The cathode looks like a cation. What's the charge on a cat? Meow, pause. Cations are positively charged. Yeah, so the cathode's positively charged too. Yay. So I hope that helps. Redox, an with the ox, cath with the red, reduction. And then anions, anodes, negative, cathodes, cation, positive. And then we'll figure out these other 2 characteristics. Okay, so we had, what did we have before? I think we had the zinc changing into zinc ions as it was dissolving and releasing 2 electrons. That's the oxidation reaction we saw previously. Well, what's happening at the anode is that the zinc metal is releasing electrons and it goes into the wire. So the anode oxidation produces electrons, and that's one of the characteristics you need to know. Anodes are the electrode where electrons are being produced. The reduction, we had the copper 2+, the blue copper ions, gaining electrons to form that black copper precipitate. It was being reduced. So at the cathode side, the electrons are being eaten up. They're being removed. So there's a decrease in negative charge. Sorry, it's a decrease in electrons. The electrons are being consumed. It's a reduction. They're being used up. Nice. Okay, this other idea. Anions migrate towards. Okay, so we got this piece of zinc metal connected to a wire, and the zinc metal, some of it is forming ions, and the electrons are leaving in the wire. Well, if the electrons are leaving, this thing's starting to become positive, right? The electrons left the metal. So that means any anions in solution, and I think in the next slide it's going to be nitrate, the anions are attracted to that positive charge. If we make a battery and we have a copper metal connected to the other side of this wire, the electrons are going to flow in the wire to the copper 2+, and then the copper will stick to that metal. The electrons are coming in. There's electrons at the electrode, and the electrons are drawing any cations in solution. The copper is actually going to be drawn towards the electrode and get those electrons. So the cation is attracted to the cathode. Excuse me. Cool. Close that out. Can we advance to the next slide? No, why not? There we go. Okay, so here's how we're going to set up a battery, a galvanic cell, at least in the laboratory. Oh, this one will change. We got copper here and silver on the right. So we got a piece of copper metal, and we got some blue copper ions in solution connected to a wire. And right here, you can actually set up a voltmeter or a multimeter, something to measure the current or the voltage, whatever you want to do. And then to the other side of the wire, connected to a piece of silver metal in a solution with silver ions. Okay, what happens? Well, the spontaneous reaction is the copper just likes to dissolve and form copper +2 ions. The copper, I should just write it. Where's my pen? The copper is going to spontaneously create copper ions and release 2 electrons. Well, copper going from a 0 oxidation number to a +2, it's increasing from 0 to +2. So we're oxidizing. That makes this the anion, the ox part. So this is the anion. Anode is what I meant to say. This makes this the anode. And electrons are released by the copper metal and flow up the wire to the other side. What happens over here? Well, this piece of silver metal is collecting electrons. There's a whole bunch of electrons on the surface now. And the silver ions in solution are attracted to the negative electrons and grab them. They gain them, and they are reduced to silver metal. Cool. Hey, it's being reduced. This is the reduction reaction. So this must be the cathode. 3 letters here, 3 letters there. Yeah, the cathode is where reduction occurs. That's where electrons are being consumed, used up. What else? The cation is being attracted to the cathode because of these electrons. What was the other thing? Oh, the charge. The cathode is like a cation. The electrons are being used up, so there's a surplus of plus charge. This is the plus end. Maybe we should think of it that way. Why are the electrons heading there? Because it's the positive electrode. Why are the electrons leaving? Because it's the negative electrons. They're the negative electrode. They're being repelled. Oh, wait, one more thing. What's this thing? It's called the salt bridge. Okay, why is it required? Well, if you've taken some physics or you played around with electronics, you know that electricity only works if you complete the circuit. So we talked about electrons starting at copper and ending up on silver. That's not a loop or a circuit. You have to go back and complete the circuit. Why? Well, electrons are leaving the copper and going over here. And as electrons accumulate over here, the silver is going to grab them and use them up. It kind of binds them. They're still here. The electrons are still here. So if you count up all the protons and electrons, you'll find that this system, metal and the solution, there's more electrons over here. And what if you count up protons and electrons over here? Well, the electrons left, there's a net positive charge over here. Wait, this whole thing's positive and this whole thing's negative? And if there's any electrons on this plate, now they're going to be attracted backwards to the positive system over here. That's not going to make electricity run. No, so instead you need this thing called a salt bridge. You put in sodium and nitrate or any inert salt that you want. And then usually you fill up with solution, you plug it. It's got a porous plug here, maybe made of ceramic that can allow ions to flow through. And the whole system can't just drain out. Sometimes you just plug this up with cotton balls, keep the solution in here, but still there can be exchange of ions and water. And so what happens is, let's start all over. Electrons release, the flow over here. The cation solutions go to electron and they're reduced. That means this system's losing cations from solution. So in the salt bridge, the sodium starts flowing over here so that this side maintains the same charge. As you use up the pluses from solution, new pluses come in from sodium. Over here, you got the negative electrode, the anode, the electrons are leaving. Cations are coming in solution. So now there's more plus charges in solution. So that's going to attract the anions, the flow through the salt bridge, so that there's more anions here to match the cations over here. And they'll keep the total charge of the solution neutral. And what is that really doing? Let's focus on the anion nitrate. It has a negative charge. It has an extra electron. So when it moves from this side to this side, it started -1, it ends with -1. It carried that extra electron to the other side. It is very much like a form of electricity. It's just carrying the extra electron as nitrate. And it completes the circuit. So electrons start here, flow in the water as electrons, get used up here, and then the nitrate ion with this negative charge leaves and goes to the other side, and now it takes the electron over here. So now you have a flow of electrons in a complete circuit, in a complete loop. It allows the current to keep flowing. You have electrical current, and it works. So the salt bridge is required to complete the circuit. Oh, I forgot to erase the screen. There we go. Okay. Why do negative ions, anions, move towards a negative electrode, anode? Well, gosh, if you say it that way, it doesn't sound right. Negative things repel negative things. How can this be true? Well, you kind of have to think it through. We call the anode the negative side, right? Yes, cations are positive, anions are negative. The anode, negative electrode, we label as a minus because electrons are coming out. But really that piece of metal, the electrode itself, is losing electrons. So that means it's positive. So the anions of solutions are attracted to the metal surface, which is positive. Cool. Why do positive cations move towards the positive cathode? Well, we label the cathode as positive because the electrons are coming into the cathode. Electrons are coming in, depositing on the surface of the electrode, the metal electrode, and cations from solution are going after those electrons and gaining them. We're doing the reduction reaction over there. So yeah, at the cathode, there's a surplus of electrons, and the cations are going to go get those electrons. They're attracted to Okay, another note-keeping scheme. So instead of drawing that whole, here, let's go back to it. Instead of drawing this every time we want to talk about electrochemistry, let's decide on a shortcut of writing this down so everyone knows what are we talking about without having to sketch this out every time. Okay, so here's the notation. At the anode side, we had copper metal becoming copper ions, releasing 2 electrons, being oxidized. At the cathode side, we had silver cations grabbing those electrons, being reduced to form silver metal. The electrons balance, charges balance, everything's good. Add them together, you get the overall reaction. Nice. If you go back 2 slides, you'll see that the copper was in 1 beaker, silver was in a 2nd beaker. So we kind of represent that here. We say, okay, in 1 beaker, the anode half cell, copper metal changes the copper 2+. So you write down the copper solid going the copper 2+ aqueous. And you put a little line in between. It kind of counts as this reaction arrow, saying copper solid becomes copper 2+. But more importantly, it's saying, hey, there's a change in phase. Phase, those are, the 4 phases of matter, 4 states of matter. Solid, liquid, gas, aqueous. That's what it's saying. It's saying, hey, we have a solid, and then we have somewhere else in the same system, aqueous. There's a change from solid to aqueous. So we put a little line here. That's 1 beaker. And then we put a double line saying, here's our salt bridge, or this is how we're going to separate. This side is 1 beaker, the second side is the other beaker. And the double line tells you how to separate it at the salt bridge. This side, the silver cations are becoming silver solid. They're gaining electrons, being reduced. That's the cathode, red, reduction. And again, going from aqueous to solid, so there's a line here. We always put the anode first, then the cathode. So alphabetical order, anode to cathode. And then that means that oxidation going to reduction, the electrons are flowing from the left side to the right. Cool, that's the standard notation. All right, let's get some practice. Where's my pen? There it is. Okay, get your microscope out, your magnifying lens, and so you can read this. It's super tiny. Write the shorthand notation for the following galvanic cell. So it's a natural cell, it just goes all by itself. So what's going on? Well, they actually tell us it's an anode, yay. So anode, then the cathode. We're trying to write the notation, anodes first. In the lab, you don't always have to have your anode on the left side of the lab bench, right? So you might have to look and see, okay, where's my reduction reaction? Because that's my anode. It's not always on the left. What's happening here though? We're told Mn, this piece of metal as a solid, is changing into, I don't know if you can read it, but it's Mn2+. And so we separate that, the aqueous from the solid, and we have our half reaction. Then there's a salt bridge that separates the manganese from these atoms, those ions, those species. What are they? Well, over here we got platinum. Wait, platinum is pretty inert. It really doesn't react. It's a great electrode that you can keep reusing. Instead, what we have, if you can read that, we have some iron 3+ atoms that are going to gain 1 electron. Ooh, it's a cathode, reduction, gaining electrons, and becoming iron 2+, sorry. That's a little better. Fe3+, gaining electron, but they're both aqueous, so there's no phase change. So you put a comma here. And then how do you get the electrons in here? What's your metal surface? It's a platinum, platinum solid. That's actually physically where your electrode is. So now let's change from aqueous solid, so we need a line, separate those 2 phases. And there we go, that's the notation. That's kind of cool. So you don't actually have to dissolve your electrode to do electrochemistry. You have 2 ions in solution, and then we just have an inert piece of metal that doesn't participate in the redox reaction. There's no side reaction here. Platinum's pretty expensive, and one reason is because it's great for making electrochemical cells. You can keep reusing the platinum. It doesn't dissolve or decompose or whatever, or cause a side reaction. Okay, we can go the other direction now. Given the following shorthand notation, write a balanced equation and give a brief description. You don't have to do this, but I'm a visual learner, so it actually will help me if I draw it out. So we're going to start over here, and it's, well, forgot to change the pen. It's alphabetic order, anode, then cathode. Where's my pen? There it is. Okay, so this is the anode, and this is the cathode, alphabetic order. So we know this is oxidation, and this one is reduction. Okay, that'll help. I'm going to draw it first. So I got my solution, and then the platinum. Okay, so we'll get used to this. Platinum is inert. It's just physically where you're going to connect your wire to. So I'll make a little loop out of that wire. And in solution, there's going to be some SN. It's actually 10 plus 2 ions that are going to give away some electrons to the platinum and become SN 4+. The electrons will be on this wire, the platinum wire, connected to a copper wire maybe. And over here we got their second beaker. And what do we have? Oh, we're using silver metal. Maybe it's a sheet of silver metal. I don't know. So let's connect the copper wire to the piece of silver. And then in solution, we got some silver cations. They're going to grab the electron and become silver metal. That's what it says here. Silver plus goes to silver metal. Oh, and then we'll need a salt bridge. So we'll get that piece of a U-shaped piece of glass tubing, fill it up with something inert, maybe sodium nitrate, plug it up with cotton balls so then they'll spill out. And that's our salt bridge. Cool. You didn't have to do that, but I don't know. It helps me. Maybe it'll help you. If you want to get through the question faster, just realize it's anode and platinum's not a reagent. It starts with SN. So balance equation, let's do it here. SN 2+ is turning into SN 4+. That's what's happening on the anode side. The cathode side, it's Ag plus becoming Ag solid. We have 2 half reactions, and it's asking for the balance equation. It wants us to balance a redox reaction. So how do we do that? Well, rewind the video and go back and take a look. We need to first separate into half reactions, balance the redox atom, balance the electrons, well, really balancing the oxidation numbers, then balance the charge by adding H+ or OH-, and then add those 2 half reactions back together so the electrons cancel out. All right, so let's do it. First balance, we got our half reactions. Separated the half reactions, cool. Balance the redox atom, 1 SN to 1 SN, good. 1 silver, balance. Okay, balance the electrons. Well, how did we go from a +2 to a +4? We must have kicked out 2 electrons. Besides, this is oxidation. This thing's gonna lose electrons. So it has to show up on the product as electrons. And yeah, if you think electron has a -1 oxidation number, a 4 minus 2 is equal to a 2. How about over here? How does silver +1 become silver with a 0 oxidation number, right? This is the natural elemental form of silver, oxidation number 0. It went from 1 down to 0. It was reduced. Reductions gaining electrons. 1 electron will take the +1, and a -1 oxidation number gives it a 0. Cool. We balance the oxidation numbers. Now let's balance charge. Okay, we have a net +2 over here, and a 4 minus 2 is a +2. Beautiful, it's already balanced. The charge, +1 and -1 is 0. Hey, that balances 0. Charge is balanced. Beautiful. There's no H's and O's to balance. Everything is balanced. Cool. Okay, so now let's add these half reactions together to get the full equation. And we have to do it so that the electrons cancel out. So the oxidation reaction's producing 2 electrons, but as written, reduction, I only have 1 electron. So I need to multiply everything by 2. So we really need to start with 2 cations, 2 electrons, and make 2 atoms of silver metal. Now we can add them together. So list all your reagents, Sn plus 2. That's the reagents on this half reaction. Reagents over here is 2 silver cations, 2 electrons. Those are all my reactants. Products, I got Sn 4 plus, 2 electrons. Those are all my products. And the other product is 2 Ag solids. And you know what? Probably should be adding my physical states. Physical states. Left out for the electrons because electrons cancel out. And make sure that no other elements are canceling out. No, any other spectators, the electrons are kind of acting like spectator ions. There we go. And if you want to write it like that, that's fine. If you want to rewrite it or erase, actually, I'm probably going to erase it. Maybe give it. There we go. There's our balanced equation for the cell reaction, the whole thing. Nice. Okay. Little summary here. Let's see, what's it say? Compartmentalizing the oxidation reduction half reactions in the half cells enables a spontaneous redox reaction to be a source of electrical energy. Fancy talk. You got your anode oxidation reaction on one side, redox cathode reaction on the other side, and by separating them, compartmentalizing, now the electrons must flow from one to the other. And then we have the salt bridge to complete the circuit. And you have an electrical circuit, and now you can harness the electrical energy to do work, electrical work. And then just summary again. One side anode is doing oxidation. Other side is doing cathode reduction. Each half cell consists of an electrode. Yeah, you need to connect your wire to a piece of metal. So you have to have an electrode. It might be platinum if your redox reaction is just consisting entirely of ions, like the Fe3 plus going to Fe2 plus. Then you need a platinum wire in there to serve as an electrode. And the half cells are joined by external wire, right, and a salt bridge. Yeah, that helps complete the circuit. Okay, batteries have voltages or cell potential. The proper term for that is the electromotive force. Okay, what is that? Well, you got the definition there. You can read it if you like, but it's essentially this. Oxidation is releasing electrons and pushing them away. Reduction is gaining electrons and pulling them in. So the push of the oxidation and the pull of the reduction is causing the circuit, the current rather, to flow. And some oxidation reactions really shove on those electrons and others don't do it so much. They have less potential to oxidize. Others are like, yeah, let's oxidize, shove those electrons. Other sides, the more prone to reduction, yeah, give me those electrons. Others like other reactions, less likely, whatever, the less of a pull. So you get different electromotive forces. So you look at the oxidation reaction and the reduction reaction, and together you can calculate something called the cell potential, or we know it better as a cell voltage. Yeah, batteries, you know, a little AA battery has a 1.5 volts. The cell potential of a battery is 1.5 volts. Standard cell potential. Okay, there's two ways, general ways you can get that push to be stronger or weaker. One is by changing your reaction. So some oxidation reactions really push electrons, others push it weakly. The other way to get the cell potential to increase is increasing your concentrations, right? Get really concentrated reagents so they really want to go. If it's really dilute, the reaction doesn't proceed very quickly, not much potential there. So you could change the concentration, or you could change the different reagents. So what we're going to do is say, okay, let's ignore the concentration effect for a minute and just say, when we make our cells, the standard way of doing it is to start with 1 molar solutions. Everybody's at 1 molar, so we don't see any changes with concentration. Oh, for people who want to be fancy and not use aqueous solutions, you can use gases in your redox reactions. But if you do, the standard way to do it is at 1 atmosphere of pressure. Also, this electromotive force is affected by temperature. I remember my chemistry teacher telling the class that, hey, I used my chemistry knowledge to help out my friends. And they're at the beach. It's a hot day. They brought a boom box, you know, portable radio running on batteries. And they're having a great time. And the radio just started dying out. It's getting quieter and quieter. And someone said, well, you got more batteries? The batteries are dying. No one had more batteries. But the teacher, who knew some chemistry, said, no, just put the radio in the shade. And sure enough, after the radio cooled down, the power came back up. Yeah, because as for the batteries, if they get hot, they get weaker. They don't have a strong electromotive force. But by putting the radio in the shade, cooled down the battery, they discovered the batteries weren't actually dead. They're just too hot. Cooling them down, the electromotive force, the voltage came back up and powered the radio. He saved the day, saved the party. Okay, this electromotive force is called the standard potential, right? We got everything standardized, 1 molar, 1 atmosphere, room temperature, 25 degrees Celsius, 298 Kelvin. And the units are gonna be volts or maybe millivolts. Cool, if you wanna get fancy with the gases, here's how you do it. You can take some H+ ions and reduce them, add electrons to form hydrogen gas, which is a non-polar molecule, so it doesn't want to dissolve in polar water. So it'll start bubbling out. You can add bubbles of hydrogen gas into a half cell, and you can make them oxidize, release the electrons to reform H+ ions and produce 2 electrons. Okay, that chemist said, yeah, let's focus on the hydrogen half cell reaction, because everyone has a source of H+. Acids are really common in the lab. We can all have this. If we want to do some electrochemistry, everybody will have some acid around, and we can do that half cell reaction. If you want to measure a voltage, you can't just have a half cell. You need the oxidation and the reduction reaction. You need the electrons to flow from one side to the other. So to get the true voltage, you need the oxidation reaction to push, the reduction to pull. And it's the 2 of them together that creates the voltage. Okay, so what we said is you can't measure one of them by itself. You need to connect it to something else. So arbitrarily, let's just assign hydrogen's half cell potential to be equal to 0 volts. It's just very arbitrary, but it's convenient. And it's just said, well, just for this, we'll just say, okay, in that case, darn it, where's my pen? There we go. In that case, if the H+ ions are being reduced, we can say the potential of that half cell, this is being reduced. This should be a red. Yeah. Okay, so we have a mistake on this slide. Wasn't me. This is a reduction reaction, right? H+ is gaining electrons. So the half cell voltage or standard potential is equal to 0 volts, just arbitrarily. And here hydrogen is losing electrons. That's the oxidation. So the oxidation potential for this hydrogen is also equal to 0 volts. We're just assigning it. That's convenient because, well, let's get out of the pen mode. Clear everything first. When we use the hydrogen, over here is a half cell, and then we're going to pick, looks like copper with copper 2+ ions, and we measure the voltage The voltage is 0.34 volts. And now what we said is, okay, connecting hydrogen, the copper gave us a real voltage measurement. But guess what? We're just going to assign hydrogen's half cell potential, the voltage, equal to 0. So when we measure 0.34, now we can just say copper, your half cell voltage is 0.34. It's just convenient. More on that in a second. First of all, why is this E pointing the wrong way? Didn't all our other cells point to the right? Yeah, because what's happening down here? Hydrogen is becoming H+. Is this hydrogen, the reagent, is it being oxidized or being reduced? It's oxidizing. H+ is losing electrons. Here's our oxidation. That's the anode. Okay, so again, anode is not always on the left-hand side of your pictures. Take a look. Here's the oxidation reaction. And ox, pair up. Here's oxidation. Electrons are flowing from here to the reduction side. Reduction side says copper ions are gaining electrons and becoming copper. This is my cathode. Labeled with a plus charge, plus sign. The anode's labeled with the minus sign. Cool. Oh, and here it is written out again. At the anode, hydrogen was being oxidized, losing electrons. At the cathode, reduction occurs. Copper is gaining electrons. Add the half reactions together, you get their overall balance equation. And then now we can calculate the cell potential, the voltage for the entire cell. We look at the half reaction potential, the E was that standard potential for hydrogen, you're being oxidized. And we said, well, we're just going to let that equal 0. The multimeter said, well, the full cell had a voltage of 0.34. And the total cell is equal to the voltage, the potentials of each half cell. So now we can actually measure the standard potential, the voltage for the copper reaction. It's 0.34. And so now that we're defining it because it's a definition, because this only works if we say that hydrogen's voltage equals 0. And now we can and say, okay, for this half reaction, no matter what you pair it with, we're going to say it's always 0.34 volts for this reaction. Let's switch it up. Take that hydrogen electrode, SHE. Did I do that? Should have. You know what? Let's go back real quick. One more detail. This one. Where's my pen? Okay. You might see SHE, she. And that stands for Standard Hydrogen Electrode. Okay, because we arbitrarily said the hydrogen reactions equal to 0 volts, sometimes we like using that in the lab. So it might say, hey, 1/2 reaction is SHE. You're like, what? Standard hydrogen electrode. It's a hydrogen reaction where the standard potential is 0 volts, whether it's oxidation or reduction. Nice. Okay, so I just want you to be aware of that. Cool. Can I have this, please? Go back. Oh, there we go. Okay. So now we're going to connect the hydrogen reaction to zinc metal. And turns out the spontaneous reaction is that it's a switch. Spontaneously, when you connect the hydrogen half cell to copper with copper ions, the copper wants to reduce. When you connect the hydrogen to zinc and zinc ions, the zinc wants to oxidize. And it's just nature's rules. Like, why is that? I don't know. It's just the property of copper and zinc. That's what they do. But now that we know that, we can just, keep track of it, I guess. You had to be told that zinc connected the hydrogen. In that case, the zinc is the one that's going to be the anode oxidizing. And the hydrogen half cell, it's going to be your cathode. It's the one that's going to be reducing. Add these together, you get your balanced overall redox reaction. You can now calculate the voltage. While you'd measure it in the lab to be 0.76, but hydrogen is assigned a value of 0. So now you can assign zinc's oxidation potential as that 0.76. Okay, so that's what was done in the lab. Now, however, we're getting some data and we want to put it in a chart. We want to publish this. And what we decide to do, or someone decided to do, is like, well, instead of having a chart with oxidation potentials and reduction potentials, let's just list only the reduction potentials. So you measured in the lab the oxidation potential, 0.76, but if you switch it, remember, if you switch it, just change the sign. So now written this way as a reduction potential, use the same number, but change it. And now you can put this number in a table with this half reaction. And that's what was done. There are bigger tables with more data, but this is plenty for us. This is all we need. And it's cool. So ranking them based on their standard potentials, the voltage, but in order from greatest to lowest, we see some pretty cool things happening. First of all, hydrogen's assigned 0, so it's always in the middle. Some things, this is reduction. So some things don't want to do this for a reaction, want to be reduced. That's these down here. Others really like being reduced, so they're higher up. And the voltage is telling you how much they want to do that. How big of a push are they doing as they reduce? Cool. More importantly are these red and blue arrows. So if you looked at all the half cells, at the top is fluorine, F2, really likes to grab 2 electrons to form fluoride ions. The half cell potential, the standard potential, is 2.87, highest on the chart here. What that tells you is that if you have some F2 around, pretty much everybody else is going to let fluorine grab its electrons. Fluorine has the highest potential of doing this, grabbing electrons and getting itself reduced. Wait, if it's getting reduced, what kind of agent is it? It's an oxidizing agent. Yeah, in fact, fluoride is one of the most powerful oxidizing agents. In fact, any container will be attacked and oxidized by fluorine gas. It's very difficult to work with fluorine gas because it pretty much oxidizes, reacts with any container you put it in. It's such a strong oxidizing agent because it wants electrons and get itself reduced. At the other end of the spectrum, way down here, I got something in the way. Let's move this. I don't know if you see that, but I do. Lithium cations like electrons to form lithium metal. Yeah, not so much. It's the least positive, it's the lowest. In fact, the reverse reaction is what's spontaneous. Lithium metal loves to release electrons. Lithium's an alkali metal. They like to give up an electron, so it has the same electron configuration as the noble gases. Excuse me. So sodium and lithium like to oxidize and release electrons to form the very stable +1 cation. So they like to give away electrons. Where are they going? To somebody else who can get reduced. So lithium is the strongest reducing agent because it likes to be oxidized. It likes to change from lithium metal to lithium cation. So cool. This is pretty powerful. By someone studying all these half reactions, getting a multimeter, measuring voltages, now we actually have a table of oxidizing and reducing agents based on the ranking. How good are they? Very powerful, very useful information. So these are reduction potentials. That's how they're listed. So the molecules are being reduced, but then ask what kind of agent are you? Fluorine, you're gaining electrons, you're being reduced. So you must be an oxidizing agent. So looking at molecules on this side, like nickel, 2+, how good an oxidizing agent? Can you oxidize 10 + 4? No, 10 + 4 is a stronger oxidizing agent. That's how the table works. So the higher up here, strong oxidizing agent. Suppose you're looking from the other point of view. Hey, sodium, how good a reducing agent are you? Can you reduce that tin? Yes. From this side, on the product side, they're better reducing agents as you go down. So sodium is a much stronger reducing agent than tin. And so if you need to reduce something, get some sodium around, that'll get the job done. Only lithium could do it better. Hydrogen peroxide, how good a reducing agent are you? Terrible, it's way up here. It can only reduce stuff that's above it. Weird. So that's a weak reducing agent. It actually likes to oxidize. Where is the oxidation reaction? There it is. Here's peroxide. It likes to grab electrons and get oxidized. Okay. What else we got? I'm going to check things. We're actually going to do some stuff I was just talking about. Let's find or rank the oxidizing agents. Who's the best oxidizing agent? Okay, you'll just need to remember this, or you'll have a table so you can go and look. Although I don't know if the table is going to have this phrase labeled on it. So you'll need to know. At the top, fluorine likes doing this reaction. What reaction? Gaining electrons, being reduced. Okay, so what kind of agent are you? Now, it's being reduced, so it's an oxidizing agent. So higher up, better oxidizer. Higher up, better oxidizer. So which one's the highest up? 1.36 is higher than 1.09, higher than 0.17. We just ranked them. This is the highest. So it's the strongest. So this one right here is the strongest. Maybe I should put first place. And then who's the weakest? Well, the lowest voltage is the weakest. This one. This is third place. That bromine's right in the middle. It earns second place. In terms of oxidizing power, so you want to order of increasing strength. Okay, so I guess you put Fe, then Br, and then Cr2O7 dichromate, right? That's increasing strength, oxidizing strength. That's what the question wanted. All right, let's do it for the other idea, reducing agents. Okay, so more negative numbers. So who's the most negative? This one. Sodium is first place in terms of reducing power. And then negative 1.66 in between. So the zinc is the weakest, it's third place. It's not very negative, not as much as the other two, and this one gets second place. So in order of increasing strength, so zinc, then aluminum, and then sodium. That's increasing strength as a reducing agent. That makes sense? That's cool. Just look at the voltages, figure out what are we talking about? Oh, reduction, more negative. What are we talking about? Oxidation, more positive. How are you going to remember that? What do you remember about oxidation numbers? If you started at 0 and you oxidize at the +2, it increases an oxidation number. That's oxidation. If you start at +2 and you go down to a +1 or a -1, you're reducing the value, that's reduction. So if you're reducing the voltage, that's reduction. If you're increasing the voltage, that's oxidation. Nice. Okay, what have we got here? More calculations. We would go to the chart and look up zinc, and it turns out the chart lists reduction potentials. So it's going to list the zinc +2 and 2 electrons as a negative 0.76. But in this half cell, we want this one to be the anode, the oxidation reaction. So we reversed it, and we have to change its sign. Copper comes straight off the table. Yeah, this is a reduction reaction. The table lists standard reduction potentials. So we just grab the number off the table as 0.34. And then the sum of the two half potentials gives you the total. So change the sign. Now it's a positive value, add them up. For the silver on the table, this is how it appears. Silver plus an electron, silver cation plus electron is being reduced. The value is 0.8. And then the copper, well, this is the form. Copper 2 plus and electrons are gaining electrons. This is the reduction. It's going to be 0.34. Well, in this half cell, we want to switch it. So we have to change the sign. We also have to balance the electrons. So we have to multiply this equation by 2. We do not change the voltage by 2. So that's something you have to remember. You can always switch them, switch the order, and you change the sign. But if you have to multiply it, you don't. It says here it's an intrinsic property, meaning that the property doesn't change. The potential, the voltage, doesn't change with quantity. It's just an inert property. Doesn't matter how much silver ion you have, the voltage, the potential, the push won't change. Guess I didn't say that right. Doesn't matter how many electrons you have. I don't know. I wish I had a better way to explain it. But you'll just have to remember, you can reverse the reaction, change the sign, but if you have to multiply the reaction, don't multiply the voltage, the standard potential. All right, learning check. Predict from the standard reduction potentials, that chart, whether PB can oxidize aluminum or copper under standard state conditions. And if it can, calculate the potential for each reaction. Okay, what are we doing? We're oxidizing. Okay, and that is how the table's listed. They are reduction potentials, meaning the molecules want to be reduced. They want to gain electrons, and they are being reduced, which means they're trying to oxidize somebody. They're good oxidizing agents. So the more positive they are, the better oxidizing agent they are. So who's the strongest oxidizer? Who's the highest positive value? Copper. Copper's the strongest oxidizing agent. So copper can oxidize lead, but the question was, hey, lead, can you oxidize copper? The answer is no. Copper is a stronger oxidizer than lead. But compare lead and aluminum, who's more positive? Well, negative 0.13 is bigger, more positive than a negative 166. So yeah, lead, you're a stronger oxidizing agent than aluminum. So you bet, down goes aluminum. Lead, you're a strong enough oxidizer. You can oxidize aluminum because aluminum's weaker. Ooh, and so now we have to calculate E0 for that reaction. Okay, so we're told that PB, you're going to oxidize. Let's start there. Aluminum, you're getting oxidized. So I need to write your equation so that there's an oxidation happening. Well, aluminum has to give up electrons. So I have to write it this way, right? So it's drawn as a reduction potential. That's from the chart. But we're going to oxidize it. So we need to flip it. So aluminum is going to become aluminum 3 plus. And we don't have to write the balance equation. Cool. So I don't have to worry about 3 electrons here. All I have to realize is aluminum is being oxidized. And this is the wrong form. I have to flip the equation and change the sign. So as aluminum gets oxidized, the half potential, the standard potential, is now a positive 1.66 volts. Lead, you're doing your job. Lead is getting itself reduced from +2 to 0. It's lowering its oxidation number, it's being reduced. And that's how it's written on a table. So lead, you're fine. 2 plus ions, you become lead metal as you gain electrons and get reduced because you're a good oxidizing agent. And so the standard cell potential for this reduction half reaction is a negative 0.13. Add them together. I don't have my calculator handy, so we're doing it by hand. Hopefully I do it right. 1.53 volts positive is the final overall voltage, the standard potential. Cool. There you go. There's still more information we can gain from these electrochemical cells, these galvanic cells. Okay, if it calculates standard cell potential of a redox reaction is positive, turns out then the reaction is spontaneous. So that's why the E cell for galvanic cell is always positive. Yeah, so I just erased it, darn it. We just added these together and got a positive, remember? Oops. Pen, please. We just did the math. Rewind the video and see how we did it. The standard potential for these two being made into a battery, a galvanic cell, has a standard potential of 0.153 volts, I think it was. More importantly, it's positive, which means it's a good battery. It will work. If you connect things together, like I don't want to take the time to do it, but suppose we said incorrectly that lead could oxidize copper, and we calculated that, the voltage would be negative. And that would be a sign like, whoa, wait, voltage is negative. That means it's not spontaneous. Yeah, it's not going to happen. Lead's not going to oxidize copper. So that's one thing you can do with the the standard potential. If it's a positive value, it's spontaneous. If it's negative, it's not spontaneous. It's a bad battery, it's not going to work. Okay, what else do we know? Oh, I said it. If your standard potential is negative, the reaction is non-spontaneous. Yep. Then we can go another step further. What else do we know about spontaneity and stuff? Okay, well, we already know, hopefully, delta G needs to be negative to be spontaneous. We said, hey, for most people, a spontaneous reaction results in a negative response. Most people don't like spontaneous things. They react negatively to it. Yeah, so if delta G, the standard free energy term, change in free energy, if that's a negative value, you know your reaction is spontaneous. And now, if the voltage, the standard potential, is positive, it's also spontaneous. So now we have two ways of detecting whether a reaction is going to be spontaneous. And I never thought about this before, but it is true. If your K equilibrium constant is greater than 1, then what's favored, reactants or products? Reactants are favored. Wait, reactants are favored? That means it should go and make products. Yeah, so if your K is greater than 1, that also identifies a spontaneous reaction. So now we have three ways of detecting whether reaction, or predicting whether reaction should be spontaneous or not. It's too bad it's so weird though. To keep them straight, always remember, for most people, a spontaneous reaction is negative. So delta G is negative. Our chart lists the powerful oxidizing agents at the top, the more positive, that tends to be more spontaneous it is. If your standard potential, E0 is positive, spontaneous. And then equilibrium constant is always products over reactants. So if products are favored, the reaction is spontaneous. K is greater than 1 when products are favored. And trouble here. There we go. Okay. Faraday constant. What do we got here? Electric charge. Oh, so Faraday went and measured 1 mole Avogadro's numbers of electrons and just said, hey, that's equal to 96,480 coulombs. Yeah, per mole. Okay, it's a conversion factor. What are we doing with that? Well, we're trying to relate Gibbs free energy, which tells about spontaneity, and the cell potential. Maybe we'll look at this one. If delta G is negative, it's spontaneous. And if the cell potential, E, is positive, it's also spontaneous. So aren't they connected? Yes. If you take the cell potential, multiply it by the number of electrons being transferred, and multiply it by this conversion factor, Faraday's constant has this value, you can actually calculate the delta G, the free energy change. Very cool. And if you have the free energy change and you divide it by the number of electrons in Faraday's constant, the conversion factor, change the sign, you can actually predict the voltage, the cell potential. Cool. Okay, so now it wants us to do it. All right, so let's go back and grab that equation. What was it? Delta G equals minus NFE. Delta G. Where's my pen? Delta G equals minus NFE. And then what's F? It was 96,000 something. Darn it. Did I write it down? I can't go back, otherwise I erase everything on the screen. Oh, no, I don't. I don't erase it. Let's go back. Can I go back? You can go back. There we go. It's 96,480. 96,480. Okay. 96,480. Faraday's constant is 96,480 coulombs per mole of electrons. Yay. Okay. What do we want to do? Cell potential E is equal to 1.10 volts. Calculate standard free energy change. Okay, well, F is equal to 96,480 coulombs per mole electrons. N is the number of moles. We want to change the sign. So how many electrons are being transferred in this reaction, in this balance equation? Well, zinc is becoming zinc 2 plus, so it's losing 2 electrons, so it's 2. Double check. Hey, copper, do you need 2 electrons to become copper 0? Yeah. So the number of electrons being transferred here is 2 electrons, 2 moles, right? The balance equation is in units of moles. 1 mole of zinc plus 1 mole of copper gives you 1 mole of copper ions, so forth. So 1 mole of zinc needs 2 moles of electrons. Okay, and the units of moles electrons cancel out. And we're left with units of C times V. And there's a big minus sign in front of this. C times V. And then we need to do that math. I want to say I did it before. Maybe, maybe not. Oh, there it is. I got 212,256 coulombs times voltage. Then I had to go look it up because I didn't see it in these PowerPoint slides. The units of coulombs times voltage is equal to a joule. Because, right, free energy is measured in either calories or joules. And then I don't like 6 sig figs when I only had 3 here. Oh, and then if you might want to change it to kilojoules. You don't have to. For the exam, please round this off to the correct number of sig figs, negative 212,000 joules, or you don't have to, but you could convert it to kilojoules. There we go. Yay. All right, another thing here. We just used that equation, delta G equals negative NFE. And then back in the previous unit, we also connected the equilibrium constant to the free energy change with this equation, negative RT, natural log of the equilibrium constant, can also calculate the free energy. So let's make them equal to each other, and you get this equation. Okay, so what do we do? Well, you can follow the math here, but I don't know why they want log. Maybe it's easier to work with log, base 10 rather than natural log. The calculator doesn't care. Maybe people do. I don't know. Anyways, watch for that. Make sure you pay attention. Is it natural log or is it base 10 log? And it's base 10 log here. R is what? 8.314. T is temperature Kelvin, but it's going to be 298. F is 96,480, I think. They're all numbers, constants. So multiply them together or divide this, multiply it, it gives you this number. And then all the units cancel out the voltage. Beautiful. Okay, so all of this simplifies to that. And now we can use it. I should probably write it down because it's probably on the next slide. There it is. I actually did write it down earlier. Yeah, learning check. Okay, let's use that equation. What was it? Let's go get the pen. I'll put it over here. The equation was the standard potential is equal to 0.0592 volts divided by the number of electrons being transferred times the log of the equilibrium constant, right? Yeah, there it is. And there's a minus. No, there's no minus sign. Let's double check. I don't want to get this wrong. Go back 2, please. Yeah, this is a positive equation, no minus sign. And I wrote it correctly. That's kind of nice that the markings on the screen stayed there. Cool. Okay. Back to pen. What does it want? Using the standard reduction potentials, calculate the equilibrium constant. Ooh, it wants K for this reaction. Okay, so then we need N and E0, the standard potential. Okay. What do you want to go after first? Want to go after the standard potential? Or do you want N? I think we can get N by itself here. We got 6 bromines going to 3 Br2 molecules. So 1 bromine starts at oxidation number -1, and 1 bromine ends up in its natural form of oxidation number 0. We're going to release 1 electron for every 1 bromine, but there's 6 of them. So N equals 6, right? 6 bromines, 6 Br minuses are going to turn into 3 Br2 molecules and release or lose 6 electrons, 1 electron per bromine. So it can go from -1 oxidation number to 0. Yeah. And it's already balanced. So we know that the dichromate, must accept or gain 6 electrons. Okay, what's the potential? Well, we need the potential for the bromine. Is this being oxidized or reduced? It's being oxidized. It's losing, the Br minus, the reagent, is losing electrons. So it's being oxidized, and that's for the bromine. And then the other one must be reduction. Is that true? Cr2O-7 is becoming chromium 3. I think the chromium is a +6 oxidation number. And it's become +3. It's being reduced in value from +3 down to 3. Yeah, so that's the chromium. All right, so let's go get those reduction potentials, oxidation potentials. Getting out of the pen mode, but don't erase, please. Good. Go up to the chart. I should have wrote the full half reaction. I think we can find it. Wow, I've gone through a lot since that table. Sorry, here it is. Can you find it? Okay, so right here is Br2. The 2 electrons become Br minus. This is a reduction reaction. But we're saying in our half cell, it's oxidizing. So you need to flip it. So right here, the bromine, we start with Br minus and we go backwards to Br2. And the voltage, and as written here, bromine being reduced, it would have been a positive 109, but it's the reverse, so it's a negative 109 volts. The chromium, oh, it's right here. Dichromate, hey, with 4 hydrogen ions, gaining 6 electrons, we predicted 6, is going to be reduced to 2 chromium +3s and 7 waters with the potential of 1.36, positive 1.36. Yeah, dichromate going to chromium +3. That's what we want. And then we go down. Sorry, like 10 slides or something, huh? Go. No. Yes. Okay. Is that true? Yeah. The dichromate, 4 H pluses, becoming 2 chromium 3s and 7 waters. Yeah. Okay. So now, pen please, we need to add those up. And we got them in the right form, meaning that this is the reduction with a plus. This is oxidation, turned out to be negative. And we add those together. Really, we're subtracting. And so I got 0.27. Yeah? Yeah. Okay. So that's this number here, 0.27 volts. Okay, let's do the math. 0.27 volts equals 0.0592 volts. Oh, the volts are going to cancel out. Divided by 6 times the natural log, times the base 10 log of the equilibrium constant. Okay, so multiply both sides by 6, divide by this number, and I got 27.36. And then I'm going to round off the 49 equals the log of K. Raise everything to the power of 10, and that cancels out the log. So the K is actually equal to 10 to this power. And if you ask your calculator to calculate that, how many sig figs do we want? Maybe our voltages. There's 3 sig figs in our voltages. Let's carry 3 sig figs. 2.32 times 10 to the positive 27 is what I calculated for the equilibrium constant. Is this spontaneous? Lots of things saying it's spontaneous. Yeah, the standard potential was a positive value, so yes, spontaneous. K is, oh my goodness, so much greater than 1. The equilibrium constant is also saying it's spontaneous. Nice. I still got the pen. Go away, pen. There we go. Okay, calculating equilibrium constant. Well, just a little review. You can use the equilibrium expression if you have the concentrations. Oh yeah, that's the equation we just saw a few minutes ago, but it was in the form of delta G equals RT ln of K. So if you had the Gibbs free energy change, you can calculate K that way. And now we got this way. Now they put in the natural log. We just used the base 10 log. Anyways, nice review page. Lots of ways of calculating the equilibrium constant. Ooh, something else. So the Nernst equation. If it has a name, it's probably important. So previous unit on thermodynamics, we also saw this equation, that if your reversible reaction is not at equilibrium, you would calculate the equilibrium, what's that called? Reaction quotient. It's like the K, but it's not at equilibrium yet, so we're calling it Q. You still calculate products divided by reactants. This is the free energy change standard if you were at standard concentrations, meaning 1 molar. But if you're not at equilibrium, it can be any concentration. So it's a free energy change that's not standard, not a little degree sign. And then we have this equation that's the same delta G here. And then you can also use the non-standard form. You put them in here, substitute them, and you crank out the Nernst equation. Oh, look at this. They changed the natural log to regular base 10 log. And you get this expression. Cool. What is this good for? Okay, well, this is when we're talking about batteries or electrolytic cell, whatever. You have cells, electrochemistry. You can go to this table and calculate the standard potential. If the standard potential, though, is with all your reagents are at 1 molar, all your gases are at 1 atmosphere, and your temperature is at 25 degrees C. Okay, we're going to keep the temperature at 25. But now you can actually calculate the actual voltage if you're not at 1 molar concentrations. Like if your battery starts going dead, the reaction's running, and your concentrations are changing. What's the actual voltage now? Well, you can see this minus sign means it's going to go down. As you start to make more products, let's just do it. Trying to overanalyze it. Anyways, this equation gives you the actual voltage if you're not at standard concentrations, standard pressure. Oh, and here it's talking about what's going to happen. The voltage of your battery or your cell, galvanic cell, can increase and it'll become more spontaneous if you have more reactant. Well, that makes sense. Add more reactant, the reaction can go and it powers the cell. Voltage increases. If you take away the product, that's going to shift the equilibrium to the right, help the reaction go. So yeah, if you remove the product, Le-Chatelier's principle says it speeds up in the forward direction. Hey, speed up forward direction is going to create more voltage or potential. And then the opposite is true. If you run out of reactant, your voltage is going to go down. If you're making too much product, voltage is going to go down. Is this the final check? No. Oh my goodness, we have a bunch of stuff left. Sorry, this video is getting pretty long. We have to take a few steps here. Let's set this up. In the interest of time, we won't work this whole thing out. You're going to use the equation. E equals E standard. Pen, please. No, not that. Darn it. Yeah, I need a break. Come on, brain, you can hold out just a little longer. You guys can pause it. Take a break yourself, then come back later. Okay, you came back, refresh. I hope so. We got E, the actual voltage, is equal to the standard potential voltage off of the chart minus 0.0592 volts divided by, where's my equation? And the number of electrons times the base 10 log of the reaction quotient. So, well, let's just do it. Go to the table and find where copper is becoming copper 2+. Where are the electrons here? They're over here. Copper, oxidation number 0 is increasing to +2. It's being oxidized. The iron is going to be changing, well, 2 iron. It's going to be changing to 2 Fe2 pluses. The oxidation number for each iron goes from +3 down to +2. It's gaining electrons. It's being reduced in value. We're going to need 2 electrons over here. Okay, this is the reduction reaction. So we can read the value right off the chart. This is an oxidation reaction, so we have to change the sign, because on the chart, it's listed as a reduction reaction. Okay, so if you go back up and look at the chart, it's several slides above us. And sorry, where are we? We're at number 8. Number 8, I worked it out earlier. There it is. Reading off the chart, copper is a 0.34, that's positive, so you have to change it to negative. The iron off of the chart is a plus 0.77. The full cell potential with standard values, 1 molar, is where you add these together, but this one's negative. So 0.77 minus 0.34 gives you a positive 43 volts. That's going to go in here. So we're supposed to calculate the potential of the cell. If you had 1 molar and you don't, it would have been 0.43 volts. How many electrons are moving? 2. Copper releases 2, and the irons grab 2. Log of Q. It's the products. Well, what are the products? The copper ion. Here's the copper ion concentration. It's 0.25. And the other product is the iron. It's at 0.20. And what do we do with that coefficient? Yeah, it becomes our exponent. So products over reactants. That's our Q or our K, the equilibrium expression. The reactants are solid copper. Okay, no solids, no liquids in your Q or your K. And then we have an exponent 2 times the iron 3+. Iron 3+. Ooh, it's tiny. 10 to the minus 4. And we square it because there's a 2 here. Okay, now it's calculator time. If you had shown all this work, I would give you all the points except for 1, because the rest of it is just math, not chemistry. So you calculate all this out. I got a positive 0.25. Oh, how many sig figs do we want? I think I only have 2. So then I got 2. It's a quarter volt. And it's smaller than 0.43. Does that make sense? I hope it does. We don't have very many reactants. Don't you want a reaction to go forward with a lot of reactants? And compared to the reactants, we have a lot more products. This is pretty much a dead cell. The voltage dropped from 43 down to, I'm sorry, 0.43 volts to 0.25. Next one, please. Consider the galvanic cell. This time to change, we're going to use a hydrogen half cell. So we're going to have pressure. So we're going to have to change things. So go back to your equilibrium. See how you deal with that. We'll do that another time, maybe in our discussion. Let's wrap up this video. Okay, let's actually look at some specific batteries. So you don't have to memorize this. This is just interesting stuff. A car battery. It's a lead storage cell. It's based on an anode reaction that deals with lead, and a cathode reaction also has lead, so it's all lead. You also need some sulfuric acid in here. So you heard about how corrosive battery acid is. Yeah, so if your car battery is leaking, that's concentrated sulfuric acid, highly corrosive, can do some damage. So be careful with your batteries if they're leaking. A dry cell battery. Okay, so the older, cheaper batteries, I'm thinking of the D-size battery, the C cells, are really cheap. They are based on zinc and manganese dioxide. And so here's the anode, here's the cathode. And the way you physically put together is you have a carbon rod, an inert electrode, and then it's touching this paste. So it is an aqueous solution, but it's not very much water. It's a very thick aqueous solution, viscous. What do we have in here? Here it is. It's a paste of manganese O2 and ammonium chloride and zinc chloride. So it actually has some of the zinc +2. Especially as it goes, the zinc is going to change into zinc ions. Where's the zinc metal? It's the container, the zinc can. So you want to know why batteries leak when they get too old? Well, if they're designed like this, the zinc metal is changing the zinc ions. It's dissolving. So the canister is actually dissolving. So yeah, you basically want to enclose a zinc can with something else that doesn't break, doesn't crack, to allow this paste to leak out. It's also creating water as the reaction goes. So it's becoming more liquid inside. No, is it? It might be. This is not the balance equation. Sorry. It's a half equation. I have to see the full equation. I think there is more water being made. So it's becoming more liquid. Yeah, so if it corrodes as the reaction goes, then it can leak. Alkaline batteries, these last better. They generally are less corrosive, but hey, it still happens. You've had alkaline batteries leak. You got zinc and manganese oxide, but it's a better design. Again, not on the exam, just interesting. NiCad, you don't see too many of these rechargeable batteries. They have memory, meaning you can drain them, recharge them only so many times. And the way they're manufactured to try and minimize that is they jelly roll it. They got alternating half cells here. That's interesting. So they got the negative electrode, positive electrode, negative electrode, positive electrode. They have a separator, which is sort of like the salt bridge. And eventually, you know, as these electrons go back and forth, right, you reverse it, you put a charge on this, you reverse the reaction, it's non-spontaneous, so you drive it by recharging your batteries. Well, you made this solid cadmium hydroxide, it's supposed to go back to cadmium metal. Is it gonna move back to where it was? No, it's just gonna, you know, as it changes, and it might diffuse away and start separating out. So eventually these fail because just of the molecules moving and getting out of this arrangement of alternating. So that explains why, or at least gives you an idea why they're not infinitely rechargeable, why they stop working. Why you have to buy a new battery for your phone. Well, they're not NiCad batteries, they're lithium-ion batteries. So here's the chemistry there. This is the first time I've seen this, actually. It doesn't actually balance this equation. It can be any number here, because it turns out the manganese dioxide combined with lots of different numbers of lithium ions to make this material. But here's your two half reactions, and this is a lithium battery and a lithium ion battery. Interesting. Anyways, not on the exam, just interesting chemistry. Fuel cell, this might be the wave of the future. Pump in some hydrogen gas, pump in some oxygen gas. Where's my pen? The spontaneous reaction is if you grab some hydrogen gas, oxygen gas, you can make water with a spark, or maybe it would be a gas because it'd be pretty hot water. You need balance it. You need two of these and two of those. Now it's balanced. That's a spontaneous reaction. Just mix them together, light a match, and kaboom! Hydrogen gas is explosive. Well, instead of exploding it and losing all that energy instantly, releasing it instantly in an explosion, let's slow it down, bring in the hydrogen here, and have the hydrogen react slowly with hydrogen ions here. Let's change the hydrogen to hydrogen ions, an electron, and oxygen. Are you becoming O minus? O2 minus rather? So you're gaining electrons. And then combine these together to form water. And as you take out the electrons from the hydrogen and you add the electrons to oxygens, you put those force those electrons to flow in a wire, create electric current, and now you have a fuel cell where you're adding the fuel of hydrogen gas and oxygen gas, and you're producing electricity cleanly. The byproduct is water. Nice. So environmentally friendly. The trick, though, is making pure hydrogen gas. You might do that from petroleum. Yikes. Okay, so that's some details that definitely need to be worked out. Corrosion. Oh, this is interesting chemistry. So if you have a nail and leave it out in the rain, eventually it rusts. What happens is that the metal surface will be damaged. So usually you expose metals to oxygen and immediately there's a reaction with air to form an oxide coating. That's what this dark color is. So if you have a piece of iron metal, it's probably got a thin layer of iron oxide on the surface. And if that gets scratched or worn off, now exposes pure iron metal. And if you have some water, that's sort of like the salt bridge. It's sort of like not the salt bridge, it's sort of like the aqueous, it is an aqueous solution. It can allow oxygen gas to react with the surface here and remove electrons and get oxidized to form water. Oxygen 0 oxidation number. In water, oxygen's a -2, it's being reduced. So you can grab electrons off of the metal and take metallic iron and make it Fe2+. So electrons are removed here. This is all iron metal, conducts electricity. So over here, the iron metal can lose its electrons, pulled away by the oxygen, and then it unsticks from the metal surface as an iron cation in this aqueous solution. And then the iron can then later react with oxygen gas to form rust, iron oxide. So that's how oxidation or rusting occurs. To prevent that, one idea is to coat your iron metal with a layer of zinc. You galvanize it. That's the process. And now, sure, you can't prevent the damage, the surface of the nail being nicked or cut, but what will happen instead of the iron turning to Fe2+, is the zinc metal changes to zinc 2+. It corrodes, but that's just on the surface. The most of the material, the nail, is all iron, but there's a thin zinc coating. And as the zinc gets corroded or dissolved away, As long as there's zinc on the metal, the zinc will continue to be corroded away and the iron won't. So you kind of sacrifice the zinc to protect the metal. And so the iron will last longer until all the zinc is gone. And then maybe you can start oxidizing the iron and corrode that. The other idea is instead of coating your iron container, like this is a water tank underground, or maybe it's a gasoline tank at a gas station, or it's a sewer tank, you can connect by a wire to some other metal that oxidizes more easily than iron. Go to the reduction table, standard reduction table, and go choose something like magnesium. So you got a big chunk, solid block of magnesium connected by a wire, and that if this gets wet and oxygen gets here, some corrosion takes place, the oxygen steals electrons from the iron, but instead of iron going to Fe2+, the electrons will come from this magnesium and force the magnesium to go to Fe2+. Because by the standard potentials, magnesium likes to lose its electrons. It's more easily oxidized. It's a better reducing agent. Very cool. Okay, electrolysis. Okay, this is where we reverse the reaction. So most of the time, actually this whole lecture has been about spontaneous reactions. Just connect it, see how it flows electrons naturally. We already said that the standard potential E will be positive if it's spontaneous. Free energy, we already know if it's negative, it's spontaneous. You can force the other reaction to happen though. That's where the signs are opposite. And then if you have a dead battery, you're at equilibrium. And when you're at equilibrium, delta G is equal to 0, excuse me. And it turns out your standard potential is also 0 at equilibrium. And that means no voltage, it's a dead battery. Here's a forcing reaction. Melt some table salt. So this is a big tub of molten salt. I think it's like 900+ degrees Celsius before you can melt it. And stick in some electrodes that don't melt at 900 whatever degrees Celsius and plug it into the wall. Power it with some electricity. Force electrons to flow through this molten salt. And you can force this reaction to go. What's the natural or spontaneous reaction? Well, that's where you take 2 atoms of sodium metal, mix it with 1 molecule of chlorine gas, and spontaneously you'll form 2 molecules of salt. You can get the reverse reaction to happen by driving it with electricity. So you can take the molten salt, Na+, Cl-, and force them back to their elemental forms. Yeah, so that's how sodium metal is produced. That's how chlorine gas is produced. And then you can take the chlorine gas and turn it into bleach. So this is a major way of making bleach. And you get some sodium metal out of it too, and you can sell that. Here's the balance equation. No, we changed it. Okay, instead of melting salt, what if we just have some dissolved salt? You can connect that to a battery. So that's what's happening here. So get a big container, saturated solution maybe of aqueous sodium chloride, and stick in 2 electrodes and drive it with a battery, stronger battery, or plug it into the wall. And what you can do is you can force the Cl- to become chlorine gas at 1 electrode. Which electrode? Well, the chlorine is going to lose electrons and get oxidized. That's the anode. So why don't we put it on this side? The anode is the negative side. So connect your battery. So the negative's here, the positive's there. And at this end, you'll see some little bubbles of chlorine gas come out. And over here, the water, it's aqueous, right? It's going to break down to form hydrogen gas, and that'll bubble out as hydrogen gas. So be careful, that's explosive. Chlorine is corrosive. It's used to make bleach. Definitely do this outdoors or in the fume hood. But connecting a battery to salt water, you can create hydrogen gas and chlorine gas. The solution also becomes basic. That's the balance equation. So you got a very concentrated sodium hydroxide solution in here. Hey, maybe that's how they make sodium hydroxide. Probably it's salt is cheap. Electrolysis water. Okay, so now just take pure water. Actually, you need to add some ions, so like the salt bridge. So maybe a little table salt, stick it to the battery, and then at one end, you'll produce one electrode. The anode, you produce oxygen gas. Cool. Store that up so that, someone who has some breathing problems, you have a canister of oxygen gas. And then at the cathode, you're going to create some hydrogen gas. Yeah, that's explosive, so be careful with that. Here's the equation we needed. Remember when we multiply coulombs times volts, we got joules? Well, thanks for nothing. This came late. We already know that. One more thing we don't know or didn't know, unless you took some physics, is the measure of current, the unit for current rather, is amperes or amps. And the coulomb is the amount of charge that's transferred when 1 coulomb flows for 1 second. I think we need to know 1 second here. Here we go. We're at slide there. I know there's 51 slides, so we're almost done. Okay, so we had the Nernst equation, and before that we had another equation that has N in it, the number of electrons. So if you know the current, multiply it by how long the current's been flowing, and you can calculate the charge, how many moles of electrons have passed through. That's your N in all these equations. Let me just grab one real quick. Where's my pen? So remember how we had, where's an equation? Oh yeah, we had E0, the standard potential, equal to 0.592 divided by N times the log of K, equilibrium constant. Okay, N is the number of electrons. So if they tell you something about current, multiply it by time in seconds, convert the time to seconds. You can calculate your N, the number of moles of electrons. That's what they're probably going to do in the very next learning check. What time is it? Yikes, it's late. A current of 30 amps is passed through an aqueous solution of NaCl for 1 hour. How much charge is passed already? Pen, please. We got 30.0 amps times how many seconds? Well, 1 hour. Let's see. In 1 hour, there's 60 minutes. And in 1 minute, there's 60 seconds. That's how you get the seconds. Hours cancel out, minutes cancel out. 1 times 60 times 60 is 360. 360 seconds. That's in the letter A. And so our current, or coulombs, is going to be 108,000 coulombs. Okay, nice. What do we want to know? We got this aqueous solution of NaCl, and it's producing some sodium hydroxide and chlorine gas. All right, let's go back and get that equation, the balance equation. Where's our aqueous solution of salt? This one. So we got two chlorine anions plus 2 waters makes chlorine gas, 1 of those, hydrogen gas, and 2 hydroxide ions. Okay, so the balance equation, pen again. Balance equation, 2Cl minus plus 2 waters goes to Cl2 plus hydrogen gas plus 2 hydroxide ions. And they want to know grams of NaOH that you can make and how many liters of Cl2. So let's first find out how many moles of these things, right? So we know the coulombs. There's a little chart over here that can help. And that's going to help me. Use Faraday as a conversion factor. Okay, so the Faraday constant, I'll put it here. Faraday is at 96 something. Looking. Where did I put it? Oh, there it is. 96, 480 coulombs per mole electrons. That's a conversion factor. So I got 108,000 coulombs. Divide that by 96, 480 coulombs per mole of electrons. Coulombs will cancel, and if you divide twice, moles goes up on top as your unit. And so the answer here is 1 point, and then I should carry a lot of sig figs because I don't want to round off yet. So 9.1, let's round off the 2. Moles of electrons. That amount of current, using Faraday's constant, produces a little more than 1 mole of electrons. Awesome. In our balance equation, 1 chlorine has a -1 oxidation number and goes to 0. So I need 1 electron for 1 chlorine atom, but I got 2. So I need 2 electrons to be released. So chlorine is going to produce Cl-, it's going to produce 2 electrons, but this whole thing's in moles. So I actually have 1.1192 moles of electrons. And in my balance equation, hiding in there is the fact that for every 2 moles of electrons, I can make 1 mole of Cl2. Right? Right, so chlorine, 1 Cl- is going to produce, well, I guess I have to do 2. It's going to produce 1 molecule of Cl2. So each chlorine needs to release an electron for a total of 2. And then it turns out the water must accept 2 electrons, right? Because this is a balanced equation. The electrons are already balanced. So there's 2 electrons being transferred. There we go. And that's going to tell me how many moles of chlorine gas is being produced. So I just divide this number by 2 and I get 0.55 something. 96. I'll round off again. Moles of Cl2. Okay, and then the hydroxide, again, it's 1.192 moles of electrons. And every time 2 electrons are released, I make 2 moles. 2 moles of hydroxide ion for every 2 electrons. Hey, that 2 divided by 2 is 1. So that's how many moles of hydroxide ion we make. Let's go to a clean page. There we go. Pen again. Okay, and now 1.1192 moles of OH minuses. That's going to be the same number of moles of NaOH that are being made here. So the balance equation is really a net ionic equation. Sodium is a spectator ion. There's sodium in here. So hydroxide ion number of moles will equal the number of moles of sodium hydroxide. And now we just have to change moles into grams. Question, want to know how many grams of NaOH. So go get the molar mass. Add up the weight of sodium, oxygen, hydrogen. It's 40 grams for every mole. And so I got, and I'm going to keep, what, 3 sig figs, I think? 44.8 grams of NaOH. Check my math. You can post in the discussion for this week. See how I did. And then now they wanted to know the volume. So you need PV equals nRT. There's other ways to calculate it. The volume, that's what they want. How many liters of chlorine gas are you making? Well, it's nRT over V, and I got 0.5596 moles of chlorine. R, that's, what is it, 0821? And R and T, I'm hoping I should go back and look, but it's probably at 25 degrees, which is 298 Kelvin. No, it's at STP. Sorry, look at my notes. So they wanted the volume of gas at STP, where the temperature is 0 degrees Celsius, which is actually 273. And the pressure is 1 atmosphere. Sorry, divide by P. Pressure is 1 atmosphere. P was on the bottom. Multiply all this out, and I got a volume equal to 12.5 liters. 12.5 liters of Cl2. Oh my goodness. That's plenty for now. I'll see you in the next video.